Hey there, and welcome. Today, we're going to tackle one of those classic physics puzzles, the concept of work. Now, it sounds simple, right? But trust me, this is an idea that trips up just about everyone. So let's dive right in and figure this thing out.
Okay, picture this. You're pushing against a solid brick wall. You're giving it everything you've got. Your muscles are burning, you're sweating, you feel completely wiped out. Then a physicist walks by, takes one look, and says, you've done absolutely zero work. What? How is that even possible? Well, that's the exact puzzle we're going to solve right now.
So, the key here isn't to just memorize a bunch of formulas. Not at all. It's about completely reframing how we think about the word work. See, in our everyday lives, work means effort, right? But in physics, it means something way more specific, and that's where all the confusion starts.
Let's start with the really simple but powerful idea. In physics, work is simply what a force does. That's it. It's not about you or your muscles or how tired you feel. It's all about an action performed by a force on an object. The force is the star of the show here, not the person or machine creating it.
And here it is. This is the single most important idea we're going to cover. If you get this, you've got work. Ready? Forget the word effort. From now on, I want you to think of work as energy transfer. That's it. When a force does work, it's either adding energy to an object or it's taking energy away. That is the secret sauce right there.
Okay, now we can look at that famous formula without being scared of it. You've probably seen it. Work equals force times displacement times the cosine of an angle we call theta. So F is the force, S is just how far the object actually moves, and theta, that's simply the angle between the direction you're pushing or pulling and the direction the object is actually going.
Now that cosine of theta part. It can look a little intimidating, I know. But its job is super simple. All it does is figure out how much of your force is actually in the same direction as the object's motion. See, physics only cares about the part of the force that's either helping the movement or fighting against it. If any part of the force is acting sideways, perpendicular to the motion, physics just ignores it. It doesn't count towards the work.
So let's really lock in this new way of thinking. Work is basically an energy transaction. A force can make an energy deposit into an object, or it can make an energy withdrawal. Thinking about it like a bank account for energy is going to make everything else click into place. All right, using this whole energy transaction idea, let's break down the three types of work you'll see: positive, negative, and, you guessed it, zero. First up, positive work. This is our energy deposit. This is what happens when your force, or at least part of it, is pointing in the same basic direction that the object is moving. You're helping it along. You're adding energy to it, and that usually means it speeds up.
So let's make this real. Say you're pulling a suitcase at the airport. You're pulling with 50 newtons of force, that's just our unit for force, at a 60-degree angle from the ground. If you pull it for 10 meters, the math tells us you've done 250 joules of positive work. And a joule, well, that's our unit for energy. So what you've really done is deposit 250 joules of energy right into that suitcase.
Okay, so if positive work is a deposit, then negative work is an energy withdrawal. This is when a force is fighting the motion, pointing in the opposite direction. The classic examples are friction or air resistance, or slamming on the brakes in your car. These forces are actively draining energy out of the object's motion, usually by turning it into heat.
So imagine a box sliding across the floor for 15 meters. Friction is fighting it the whole way, with a force of 20 newtons. That friction has done negative 300 joules of work. It has literally withdrawn 300 joules of energy from the box, turning it into heat. The kind that would actually warm up the bottom of the box and the floor just a little bit.
And this brings us right back to pushing that wall. Zero work means there's no energy transfer, no deposit, no withdrawal. And this happens for two big reasons. One, the object doesn't move. The displacement is zero, that's our wall. Or two, the force you're applying is perfectly perpendicular at a 90-degree angle to the direction of motion.
The absolute classic example of this is a satellite orbiting the Earth. Think about it. Gravity is constantly pulling the satellite straight down, towards the center of the planet. But the satellite is moving forward, tangent to its circular path. That means the force of gravity and the direction of motion are always at a perfect 90-degree angle to each other. And what's the cosine of 90 degrees? It's zero. So gravity does zero work on the satellite. It's essential for changing the satellite's direction, but it's not making it speed up or slow down. No energy transfer.
Okay, so we've got this great idea. Work is energy transfer.
But is it just a nice analogy? Nope. Let's lock it down with one of the coolest and most powerful rules in all of physics.
It's called the work-energy theorem, and it's so beautifully simple. It says that the total work done on an object, that's adding up the work from every single force acting on it, is exactly equal to the change in its kinetic energy. And remember, kinetic energy is just the energy of motion. So see, work isn't just like an energy transfer. It is the energy transfer, measured precisely.
And this gives us a fantastic gut check. If you see something speeding up, you absolutely know that the total, or net, work on it was positive. An energy deposit was made. And if you see something slowing down, the net work had to be negative, an energy withdrawal. The two are just locked together. It's that simple.
Okay, let's put this theorem to work. Imagine a 1,000-kilogram car, about average size, cruising along at 20 meters per second. The driver slams on the brakes and screeches to a halt. The question is, exactly how much work did the braking force do?
Well, we can calculate the car's starting kinetic energy, its energy of motion, and it turns out to be 200,000 joules. When it stops, its kinetic energy is 0, right? So the change is negative 200,000 joules. And according to our theorem, the net work must be exactly that. The brakes had to do a massive energy withdrawal of 200,000 joules to get that car stopped.
All right, now that we have this really solid energy transfer framework, let's go back and bust some of those common myths about work that trip people up.
First myth, if I'm tired, I must have done work. Nope, pushing on that wall burns your body's own energy for sure. But if the wall doesn't move, the mechanical work on the wall is 0. Next myth, if there's a force, there must be work. Again, nope. Just think about our satellite. Gravity is a huge force, but it's doing 0 work. And the last big one, if an object's speed is constant, no work is happening. Well, not quite. It means the net work is 0. You could be pulling a crate doing positive work, while friction is doing the exact same amount of negative work. The energy deposit and withdrawal cancel each other out perfectly, so the speed doesn't change.
All right, to wrap this all up, I've got a little brain teaser for you. Imagine a tetherball whipping around a pole. Now, what if you start pulling the string down through the post, so the rope gets shorter and the ball spirals inward? Does the ball's kinetic energy change? Does it speed up? Think about the force you're using to pull the string. Is that force doing positive, negative, or 0 work on the ball? I'll let you chew on that one. Thanks for diving into this with me.